3.2, differentiability.
I only got to diff. I didn't know this on the rest.
17 letters.
That's a doozy. I was thinking more.
That's
how old I am too.
I bet that's how cold I am. You're 17 letters old?
Yes, I am. I'm 17 letters old.
Alright, so f prime of a, so the derivative of the function at a can fail to exist. I'm sure that's exactly what you wanted to hear.
I mean, like, if it's less work if it doesn't exist, then yes.
I don't know about that.
Okay, so then.
Alright, so functions won't have a derivative at point P of A and F of A where slopes of secant lines which would be f of x minus f of a over x minus a fail to approach the limit as x approaches a. Okay. If a graph has one of the following four things, it will fail to have a derivative at the point. So basically there's going to be four options for this. So I'm just going to basically explain them, draw a little like mini graph of what it would look like, and then go from there. Anyway, so the first one is a corner. And this is where the one-sided derivatives differ. So an example of this is going to be an absolute value function. So in this case, there would be a corner at x equals 0. And it kind of makes sense because, I mean, it does like v into a point. The next one is going to be a cusp. Which is where the slopes of secant lines approach infinity from one side and negative infinity from the other side. So this one's going to kind of look the same, but it's going to be a little bit different. So it kind of looks like those little birds you draw as a kid. Like, well, this one does. Well, that's fair. I can't either. We've seen that by evidence through my airplanes in physics class. But the next one is where there is a vertical tangent which is where the slope of secant lines approach either infinity or negative infinity from both sides. And just for reference, this is the graph of x to the 2/3 up here, in case you were wondering. I mean, we know the top one was the absolute value of x, but so something like this. So there's a vertical tangent at x equals 0. And this is the graph of the cube root of x. So in this particular scenario, there would have been a vertical, or it would have been the slope of the secant line would have been infinity, or would have been at infinity for this one. And then the last one is discontinuity. And this is where one or both sides of one-sided derivatives are non-existent. And so this would be like a step function. But this can be the other types too, like we had with, infinite discontinuity and all that, so. All right, so the next thing, differentiability. Bet you didn't think you were going to have to write that twice today. Implies local linearity. And you're probably like, what is that? So I'll tell you. Huh?
I said you read my mind.
So local linearity is a function that is differentiable at A that closely resembles its own tangent line close to A. So your book has a way to explain this slightly different than that, and it says that in terms of your graphing calculator, differentiable curves will quote unquote straighten out when we zoom them in or I guess I should say, hold on, when we zoom in on them at a point of differentiability. Now, you might be excited to find out that your calculator can do derivatives at a point for you. Doesn't mean you get to do that, but I am going to show you how. So, numerical derivatives on a calculator. So we've already seen, so I'm going to do a little bit of backtracking and then I'll actually show you the calculator thing. But we've already seen the difference quotient for approximating f prime of A. And so that was f of A plus H minus f of A over H. But instead, now what we have, or another thing that we can use to give us a better approximation, is going to be the symmetric difference quotient. And so this is going to be f of a plus h minus f of a minus h all over 2h. So a little bit of a difference. And specifically, this is used to compute the slope between two nearby points on opposite sides of A. And so this approximation is going to be close enough to be used as a substitute for the derivative at a point in most applications. And so now you might want to actually know how to do this on your calculator. So we have a numerical derivative of f at A. And so we denote this, can't spell. So we denote NDER f of x, comma A. And this is the number. Now you're probably thinking, oh goody, we just get to type stuff in. Well, there's still a formula that goes with it. F of A plus 0.001 minus F of A minus 0.001 all over 0.002. Now, if we wanted that specifically at a point A, if we just wanted the numerical derivative of f, it would be f of x plus 0.001 minus f of x minus 0.001 all over 0.002. Now, your calculator probably is actually going to call this NDERIV, and you would get to that under math, and then it's number 8. And basically at that point, it's going to bring up something that looks like this.
Yeah, because then we did like the what do they call integrals or something?
That's a different one, but yeah.
Formula?
Yeah.
So yeah, it's just, yeah.
But yes, we had it was probably NINT or something like that.
Yeah.
But yes, we do.
I like
So you can plug in pretty much any problem, and your calculator can figure it out for you. And basically what your calculator is doing is running it using these formulas. But the formulas allow us to be able to do the same thing by hand. So, and it's a good enough approximation that we can use it. All right, one more note thing. Or well, I say one more topic of the notes. So, differentiability. Bet you really didn't think you were going to have to write that 4 times today.
I should be paid every time.
Good compensation.
So, differentiability implies continuity. And so, there's a theorem for this. So, theorem 1. If f has a derivative at x is equal to a, then f is continuous at x is equal to a. And then I guess it's not exactly the same topic, but we have another theorem. So anyways, finishing with 2 theorems. So intermediate value theorem. For derivatives. And in the book, this is theorem 2. So the numbers of the theorems are just what they are in the book. That's not like, their name or whatever. If A and B are any 2 points in an interval on which f is differentiable, then f prime takes on every value between f prime of A and f prime of B. All right, so that's where we are going to stop for today because, one, we don't have that much time and I don't want to start and only do like 1 or 2 examples. So we'll do examples tomorrow.